The massive star generates intense solar activities, including solar flares or coronal mass ejection, which can impact satellite systems and power grids. Missions like Aditya L-1 studies the outer atmosphere to better understand this fundamental process. So we welcome today's speaker, Dr. Sneha Pandit, who is distinguished astrophysicist currently serving as postdoc researcher in IUCAA, Inter-University Center for Astronomy and Astrophysics in Pune. She has been driven by profound motivation to understand the origin of life and the evolution of the universe. She has earned her PhD in theoretical astrophysics from University of Oslo, Norway in 2023, where she specialized in solar stellar activities using the Atacama Large Millimeter Submillimeter Array. Her current research focus on the investigation of magnetic switchback in solar corona and fundamental Sun-Earth connections. Dr. Sneha Pandit's academic journey is marked by excellence, including BS, MS, dual degree from ISAR Bhopal, and second rank in Mumbai division in her education. She is prolific researcher with multiple publications in prestigious journals like Astronomy and Astrophysics. Beyond her technical expertise in programming language like Python, Fortran, he is dedicated educator as well as outreach leader. He has served as outreach coordinator for INDUS, that's Indian Network for Dynamic and Unified Solar Physics, and has designed many hands-on experiments for school on optical astronomy techniques. Beyond her multi-faced personality extends her far beyond research lab. She is certified cricket umpire who has played at an international level in Oslo, as well as Visharad graduate in Bharatnatyam and performed across India, China, and North. So today she is going to deliver us the lecture on importance of Aditya L-1 in study of the sun. This basically helps us to discover the secrets of our star with Aditya L-1, India's first dedicated solar observatory operating from a unique Sun-Earth L1 point, that is the Lagrangian point. It provides us a continuous 24 by 7 observation of Sun's atmosphere, equipped with advanced scientific instruments to study the Sun's outer layers like corona and chromosphere, where Sneha would be talking much in detail about it. So welcome everyone, and I would ask Sneha to start with her session now. Over to you, Sneha. Yes, Sneha, please go ahead.
Can you see my screen? Yeah? Okay. So I cannot see any thumbs up or anything anymore.
No, you have to, Sneha, you have to click on show my screen anyway. You're still not able to see your screen.
Okay. Okay. Can you see this now? No.
So it is the multiple screens.
Maybe now. Can you see it?
Still to come.
Yes.
Yeah, make it full
Yeah.
presentation.
You see it in the full screen now?
No, not yet. We are seeing your only the presentation part, not on the full screen.
So what I have to do is first maybe now you see it. I think.
Yes.
Yes. Okay.
Can you just click on hide below?
Yeah. Yeah?
Yes, all good now. All yours now.
Okay. Hello everyone. I'm Sneha Pandit. And as mentioned by Mangesh sir, I'm going to talk about this topic, the importance of Aditya L-1 in the study of the sun. So this is like a quick motivation behind why do we need to study any star for that matter, and since we live near the sun, why do we study the sun? So since like very beginning of the time when human beings started to think, one of the questions that they were very passionate about was that if we are alone in the universe or not. So two possibilities exist: either we are alone in the universe or we are not alone in the universe. It's a binary question, yes or no, and both are equally terrifying. So because if we are, then it's kind of a glitch that there is life, there are chemicals coming together into cells coming together into life forms which can have neural pathways which are able to comprehend the chemicals and cells and the other things made of other kind of chemicals and cells, and things which are not made of cells but only chemicals by themselves. So that is like such a weird thing to think about, that we are alone. Or if we are not alone and there are other beings, other kind of life forms in other places, in other galaxies or other stellar systems, then either we have to prepare to greet them, either cordially or a kind of a interstellar war or something like that, or they feel that we are not good enough. They know about us and they just feel like we are something very rudimentary and we have not achieved enough as humanity, as a community. And all of these possibilities are equally terrifying. So this is a quote by Arthur C. Clarke. He was a pioneering science popularizer from the US in 1960s, 70s, when science popularization became more common than before. So we start on this note. So any or most of the stellar physics research goes into this paradigm of the habitability. So habitability is controlled by the host star mostly. So if we are not alone in the universe, we want to look at exoplanets roam around the host stars basically govern almost all kind of pathways to habitability, one of which is star planet interaction, which we'll go into detail. We are not going to talk about possibility of atmosphere or stars being the source of energy or source of life for the planet around it. But we'll talk about these two things: star planet interaction and space weather in the talk, in the initial part of the talk at least. So to understand our star, we should basically just know a couple of uh, basic physics about our star. So any star has some kind of structure. Um, so in the case of our sun, we have the core where the energy is produced via nuclear reactions. That energy is radiated away, so we have radiative zone. Maybe I can, yeah. So in the core, the energy is formed, then it's radiative away in the radiative zone. Then there is a very thin layer between the radiative zone and the convection zone. So there are these three different ways that energy can transfer. And conduction cannot happen because it usually happens from on the very rigid bodies, which is like solids or liquids mostly. So since sun is a ball of gas, convection and radiation are mostly the ways where energy can transport. So the temperature of the core is very high. It is multi-million degrees. And then eventually, as we are going away from the source of energy, the temperature decreases. As we are, so the density of this whole ball of gas is so high that when a photon wants to escape this gas, it basically cannot. So usually when I have to talk about this, I give an example of very crowded station, like maybe the other station, where a person wants to knows like they have to reach this platform, but they cannot go in straight line. They have to avoid all the people and navigate through to reach that particular platform. So that's what happens with the photon. It has to, like, it just collides with a lot of other photons, particles in the gas, and it just cannot get out directly. So if a photon doesn't get out, we actually cannot see anything, because photon is the uh, is the information that is going to come out. So if the photon is not coming out, we are not going to be able to see anything inside a layer. So that layer is called photosphere, from where the photons can escape. Now the photosphere is the innermost layer of the sun that we can actually visually see. So that layer has a temperature of around 6,000 degrees Celsius. Uh, all the information that we have from anything which is inside the photosphere is scientifically derived, obviously. So there are different ways. So there is some a field in solar physics called helioseismology, which is seismology meaning the understanding of waves. So there are different waves happening inside the ball of the photosphere. For example, we have earthquakes, and because of those waves, we can understand how Earth has a core and Earth has a mantle, and everything like lava and so on inside the Earth, and we estimate the density of the Earth and temperature of the core and so on. So similarly, helioseismologists, the people who study this interiors of the sun, they estimate these information of radiative zone, tachocline, and so on that I talked about. But people like me who are optical astronomers, we actually rely on photons. So the photons that escape from photosphere and onwards, that we see using different observatories, and then we use that to derive information of those layers and Celsius. After that, obviously, since we are coming away from this source of energy, source of heat, the temperature is supposed to decrease. It decreases still in another layer called chromosphere, which is right above the photosphere. It's called chromosphere because chromo means color in Greek. And what they saw for the first time, that layer, they saw it into a wavelength which is near red. So they wanted to call it a red colored sphere, but it eventually it became the colored sphere, and it is the name of that layer since then. So in that layer, the temperature decreases till 4,000 Kelvin, but eventually there is a fine region between there where the temperature starts to increase and goes to 10 to 20,000 Kelvin. And eventually, when we are outside the chromosphere, the plasma is even rarer in a layer called corona. Again, fun fact, it's called corona because it has this kind of, protrudings outside. And that kind of looks like a crown's protrudings on a king's or queen's crown. And it's the same reason why coronavirus was called coronavirus, because it has these crown like protrudings outside. So yeah, anything that has protrudings, spherical, weirdly shaped object is apparently called corona. So the corona of the sun eventually goes to 1 to 2 million degrees Celsius. So it's kind of counterintuitive that we are going away from the source of heat. The plasma or the gas from which the sun is made is getting rarer and rarer, but the temperature is increasing. So this is the one of the puzzles that solar physicists want to solve, and it's called the coronal heating problem. So that is one information about the sun. Another thing is that sun is not a rigid sphere. So when we think about rotation of a spherical body, like earth rotates around itself in one day, but sun has something called differential rotation. So what happens is the uh, equator of the sun rotates faster than the pole, and because of that, the all this plasma is in a way misplaced. For example, if equator of the earth rotated faster than the pole, then for example, for us, the map of India, the south India would be rotate faster than the north India because it's farther away from the equator. And then like the shape of the surface of the earth, or everything which is lying on the earth, would constantly change because of that. And that's what happens in the sun. Now, one more thing is that sun is made of something called plasma that I have been saying. So what is plasma? It is a gas in which the positive and negative polarities are separate. So atom is made of a positive nucleus and negative electrons around it. If we provide heat to this atom, then these or heat or any other kind of energy to this atom, then these electrons will basically get energized and move away from the positive nucleus. So then the polarities will separate. um, so that's what happens in a plasma. And then if we keep on providing heat, eventually all the electrons will separate from the nuclei. And these both of these kind of charged particles will start to move. And now charged particles moving will create electricity. And varying electricity, if these particles are moving with varying velocity, then the electricity amount of electricity will vary, and that will basically create magnetic fields. So if the equator is moving at different speed than the pole, then this plasma has inherently different motions, and that kind of creates entangled magnetic fields. And why is this why does the differential rotation kind of sustains, is one of the another puzzles in solar physics that scientists want to solve. So a couple of more information that we need about the sun before we get into the main topic of the talk is that these different layers that I talked about, photosphere, chromosphere, corona, they look entirely different when we are looking using telescopes. So photosphere has these peculiar features called sunspots, and then there are these umbra regions around sunspots. Then there is something called granulation, which occurs because of the convection zone below the photosphere. On the other hand, chromosphere has a lot of magnetic loops, which are obviously smaller than the loops in the corona, but which stand tall, and we can observe those using the instrumentation that we have currently. And obviously corona extends very very far away because it's the supposed to be the outermost layer. And eventually corona drives the solar wind, which reaches the planets, like till all the planets. So the sphere of influence of the sun is called heliosphere. So we are inside heliosphere, like all the planets are inside heliosphere. And the solar wind goes like in entire of the heliosphere. So eventually after coronal heights, at a particular point the density drops really low, the plasma density. And at that time we can say that the sun is over, but the influence of the sun is not over. So that plasma still continues, and it is like filling all the heliosphere. Yeah, this is just to summarize the coronal heating problem. So from the core to the surface, so surface is at somewhere near 6000 ish Kelvin, and then we go to chromosphere. We have temperature minimum in the sun, and then the temperature increases again and to multi-million degree corona. And in this, it's very simple plot where we can see like one dimensional temperature increase, where there is this transition region where the temperature increases very suddenly, but the density consistently drops. So this is the puzzle that we want to solve. Okay. um, so most of the initial movies that I'm showing are from an observatory by NASA. The observatory is called Solar Dynamic Observatory, and it has several instruments on top of it, out of which there is this atmospheric imaging assembly, and it captures corona. So there are different wavelengths in which, so sun is, or any star for that matter, is emitting very different, all kind of wavelengths, starting from gamma rays to radio waves. And it can peak at particular wavelength, but the entire black body spectrum can be seen coming from the sun. So any star has that. And when we are talking about a white dwarf or a red giant or a blue star, we call sun a yellow star. Why do we call them in particular of those colors? Their black body spectrum peaks in those wavelengths, where we can call this, we are very limited in spectrum, that we can only see 300 nanometers range with our eyes. So the coronal emission is usually very ultraviolet, and also infrared, which we cannot see. And we'll come to that point. But so the point being, atmospheric imaging assembly has been functional from 2010, and then it has been observing the sun continuously. but only so we know quite a lot of information about corona using these observations because it's continuous observations. But for chromospheric wavelengths, we are quite limited. Okay, so this is another composite image using three different coronal wavelengths where we can see something called a coronal hole, from which a continuous large stream of solar wind can come out. And you can also see like other kind of features like some kind of eruptions, movement of plasma along these ribbon like structures which are magnetic lines, magnetic field lines, and also the rotation of the sun. So this is what we have from the SDOAI observatory. One complementary thing to the discussion that we're having is the complexity of the magnetic field of the sun. So when we think about magnetic field, we usually think of a bare magnet in relation with the Earth's magnetic field, because Earth is a very simple dipolar magnetic field. So we have like two poles and the polarities slightly off from the geographical poles, but it works quite simply. Whereas for the sun, since it's a ball of gas and it is also moving differentially, the magnetic fields can be quite complex. So this is one of the renderings from a code of the, so the background that we see like black and white polarities is observed, and then using something called magnetohydrodynamics, so that is a set of equations that is used to study stellar plasma. So using these MHD magnetohydrodynamics equations, these magnetic field lines are predicted. So these can be quite different for different times because the things on the surfaces of the sun are moving all the time. So this is just to show the complexity of solar magnetic field, and these are basically imaginary. So we can see these using observations because there is plasma going these magnetic field lines and emitting photons during their motion. So we can, using those photons, we can see like in what directions the plasma is moving, and we understand that this could be the magnetic structures, but it's still not as uh, direct or simple in all the layers of the sun. One more thing is that these magnetic structures are huge. So for reference, we have the earth here, and this is just a small part on the coronal layer of the sun, which has like several earth's like sized magnetic loops. um, Now the thing is, these kind of loops, if they stay on the sun, we love to observe them, but these kind of loops can erupt. So the magnetic polarities can change. There can happen something called magnetic reconnection. That means that several polarities can just cross each other, and the plasma on top of it can just get released, and that will reach us. One detour in this is the solar activity cycle. So currently we are at the peak of the solar activity in the current cycle, but since it's not complete, I'll show the previous cycle. So the solar activity or the occurrence of these sunspots, frequency of the flares, amount of turbulence within the on the surfaces of the sun, that can change over time. Usually, approximately, it is supposed to be 11 years cycle. So the if we see like in 2020 or 2010, the disk is almost clean, like there is not much happening. But when we are in 2014, 2015, or currently at 2025, 2026, we are at this very complicated magnetic structure on the surfaces of the sun, where there are way more sunspots occurring, way more flares occurring, and so on. So firstly, why does this happen? How exactly does this happen? And secondly, there can be variability within this. So there can be cycles which are as short as 8.5 to 9 years, as long as 13 to 17 years. And there can be some times when the solar activity doesn't change for a decade. That has happened in earlier times when they started observing the solar disk continuously. So that was called Maunder minimum. That was in 17th century. So there can be variability in the active events that we see on the sun. Now we see the sun every day, which is very close to us, and we have studied it for so long. We, in the sense, the humanity has studied it for so long that we know it in like quite details, as I have been explaining. But when we are talking about habitability on other planets, their host stars can have these kind of variabilities in their cycles. Their host stars can have all the features basically that we talked about the sun. And if we are not very sure about the activity cycle or the variability in the activity cycle for that star, we are not even, so this activity cycle for sun is of nearly a decade, but for other stars it can be as short as a few days, as long as a few centuries. So we don't know which part in the activity cycle we are looking at for those stars. And then if we predict habitability based on the current activity, we might be under predicting or over predicting the safety in the on the planet, because it could be in this phase where we are currently watching and understanding, observing that star. But then when it is in its peak activity, it can be way more turbulent and way more dangerous to for the exoplanet. So learning about the activity cycle is quite important, is what I wanted to get across. Okay. The other, so star planet interaction basically has a lot of facets to it. Obviously, they interact with each other gravitationally, but also using the solar wind plasma, and so that chemically as well, and energetically as well. The star provides the energy, and magnetically as well, because the magnetic field of the Earth is quite nicely oriented along with across the sun, so that we don't get too much impact of the solar active events. So that naturally leads us to the topic of space weather. So maybe can we can somebody tell me, if they know, how many satellites are around the Earth as of now, which are functional, because there can be a lot of space debris from before, but which are useful and functional. Oi. If not, I can quickly go forward. So usually at any given point, around 15,000 satellites are around Earth which are functional, and there can be more or less, but it's quite a lot of number, and we are entirely dependent on satellite communication. We use internet, we use phones, we use internet for everything as of now, and we use GPS, and they are also used in defense and so on. So it's a very crucial uh, technology as of now that we would like to preserve. But not only satellites, space weather can also affect the electric grids. So the thing is, the plasma that comes out of the sun is electrically charged and magnetically charged. So if it somehow penetrates the atmosphere of the Earth and reaches our electric grids, which are like overhead lines, then it can suddenly surge into the and basically destroy the electric grid. And that has happened twice. So once in 1972 and once in 1978, in mostly in the northern part of the Earth, because that is where the magnetic poles, like near the poles, because the magnetic poles kind of pull these charged particles, whereas near equator mostly we are more secured in this regards. So why is that? Because when anything from that, so this is cartoon, this is not to scale, like this is very artistic impression of what it can be. So solar wind, solar flare, whatever comes from the sun, it will go in all directions. But if it gets trapped in the Earth's magnetic polarities, then we can see the northern lights, or these kind of problematic events can also occur. Mostly at the equator, since we have like the magnetosheath around, the wind kind of follows the magnetic field line of the Earth at that point, and that's why these events can usually occur near the poles. So what are these events basically? So this is one of the coronal mass ejections that we can see. um, there is one more, I think. Yeah. So you can see something happening here, and suddenly a huge mass from the sun is thrown out, and that kind of mass can basically, if it reaches the right time, it can destroy the satellites. So there was this event in December 2023, when Starlink sent a set of satellites. They do these kind of hexagonal thing in the orbit, and all of those near 50 satellites got destroyed the very next day because of this kind of event. So we would like to know, we would like to predict this kind of activity, which is also a field of research, but it is quite complicated. It's not that straightforward to understand how this happens. Okay. So I got lucky. It's just a detour. So this is tiny me during my PhD time, since I was in Norway and this kind of activity was happening. I could see the northern lights, and it was very surreal. So I think this is one of the only perks of having solar activity around, that we can have this beautiful aurora in front of us. Okay. So now we come to the question at hand. There are different kinds of observatories. Few are in the space, few are on the Earth. Why would we have these kind of different observatories? Firstly, and secondly, why is Aditya L-1 important? Yeah. So I will uh, tell which are which because it's quicker. So Parker Solar Probe is very close to the sun. It's in a very different orbit. Solar Dynamic Observatory, the one that I showed, the images and movies that I showed were from this one. It's also in the space. And then Kodaikanal is on top of a hill in India. There is Udaipur Observatory, which is near a lake in Udaipur. Um, there is EST, European Solar Telescope. It is on top of a hill on an island near the water. In Hawaii, there is another solar telescope which is also near water. In La Palma as well, there is a telescope which is, La Palma is again an island. So that telescope is also near water. So when we have an observatory, there is one more in India in Ladakh that is also near a lake, and also on its latitude is quite high. Also altitude is quite high. So why is that? There are several reasons. Firstly, we want the noise to be minimum. So on top of Earth, there is like a huge atmosphere, in which there is air, there is dust, and so on, which can scatter the photons. So that can introduce noise, and we don't want noise. So one way to avoid this is to send the observatory in the space. So we avoid all the noise from the atmosphere. So inherent photon noise and noise because of the instrumentation and so on, we cannot avoid anyway. But at least we skip the atmospheric noise in this case. In addition, there is one more reason to send observatories in space that we'll come to later. We are currently talking about noise, but in space, what happens? The amount of information that is sent, relaying through the antennas, like from satellite to antennas and through the chain, it's in packets and it's a bit smaller. And even relaying information through the atmosphere can introduce noise, and that sending it in smaller pockets kind of is limits the amount of observations we can have. On the other hand, on Earth, we don't have that limitation, but so we can go and see and observe for however long, and use that data immediately using hard disk or whatever. But the atmospheric noise comes into the picture, and for that, having either we go on top of a hill like in Ladakh or Kodaikanal, uh, or EST, so that we have like a rarer atmosphere and slightly less amount of atmosphere on top of the observatory. Or we go near water, like in Udaipur or and so on, so that water can cool the column of atmosphere on top of it and reduce the heat and motion of particles because of heat. That reduces the noise. So one of the major problems we can say, or puzzles we can say, in solar physics right now, is that we have so much data, because we have been like, people have been studying sun for 400 years now, but out of which there is very little data that can be scientifically accessed, because there is so much noise, there is so much other kind of unuseful observations, that we have too much data, at the same time we have too little data, so is one of the noise reduction is one of the challenges that we face. So we will have this mid or towards the end, mostly 60-70% of the talk is done. So this is the summary of all the current problems in solar physics, and then we will go to how one of few of these can be addressed using Aditya L-1. So we touched upon coronal heating problem. We talked about the variability in the solar or stellar activity, just to remind. We talked about the solar wind prediction, space weather prediction, even the coronal mass ejection and so on prediction, so that we understand how space weather behaves for better satellites. We talked about generation and sustenance of magnetic field, so that is called solar dynamo inside the core of the sun, and imagine and noise reduction. Okay. Last piece of information that we need is that our atmosphere, so we mostly study these or understand, talk about these electromagnetic spectrum in maybe 11th 12th, I forgot, but we know that there are different wavelengths corresponding to different frequencies uh, that correspond the entirety of the electromagnetic spectrum, out of which visible light is very small amount of from that. Visible light can penetrate through the atmosphere, but most of the ultraviolet, X-ray, and gamma rays at our atmosphere is opaque too. Most of the infrared, our atmosphere is opaque. Most of the microwaves, our atmosphere is opaque. That's why we use radio waves for most of the telecommunication. And then again, very high frequency radio waves are, low frequency radio waves. The atmosphere is again opaque to that. So, uh, from the sun, the entirety of the spectrum is produced at different intensities maybe, but we can see like all of these if we were not inside the earth. So if we want to see information from these regions which are near to the optical, but because the peak of the sun is near yellow, because we call the sun a yellow star, so these are also quite strong, which are near to the optical, and we would like to see these. So the chromospheric region of the sun produces these wavelengths, and to see these we need to go outside the atmosphere. And these are the wavelengths in which there are several instruments on board Aditya L-1, which are from these wavelengths, which are complementary to the currently established space and earth-based observatories. So earth-based observatories can observe mostly in this region. The SDO observatory, or there is another one, there are several others called IRIS and so on, which can observe in few of these wavelengths, near X-ray, near ultraviolet, near infrared. But then there are several other wavelengths in which the sun emits the photons, which we were not able to see from before, but with Aditya L-1 we can now see those. Okay. So Aditya L-1 has many instruments on board it. So there is one called visible emission line coronagraph. So corona being the outermost layer, usually the visible emission is coming predominantly photosphere, and it is more intense from the photosphere, so we cannot see corona very clearly usually. So we need to kind of eclipse the disk of the sun to see the coronal visible emission. So So that is one of the instruments. There are these X-ray spectrometers. So we already know that none of the X-rays can penetrate the atmosphere. So we need to go outside, and this is one of the very useful soft X-ray. And then we also have hard X-ray, high energy X-ray, uh, coming from the observed on the sun. We have plasma analyzer. So the particles that are coming from the sun, like the ions, those can be captured in the instrument and analyzed for their like charge and magnetic field and velocity and so on. So this plasma analyzer package of Aditya Papa, that gives us the information of the solar wind composition. There are magnetometers. So the magnetic field at L1 we can study using this instrument. So other kind of, like, ions can be of different kinds. So protons and alpha particles can be studied using aspects, and other kind of energetic particles, high energy ions, those are also studied using, like, this is like one payload with two instruments on it. This is how the, like, different instruments are placed at different places on the Aditya L-1. So all of these were placed, and the instrument was sent to the location L1. Why is that? So these are Lagrange locations where the gravitationally sun and earth gravitational fields are balanced per se. So less energy is consumed keeping these instruments at these places. So L1 is the most convenient one because L3 is so far away. Sending information from this data, so from this place to Earth, would be like a very difficult job. Also, it will cross the sun and get polluted. From this place, Earth will always eclipse the sun. So there are other instruments which actually want Earth to eclipse the sun so that they can see the other less intense stars. So those are kept at L2 usually. But if we want to see the sun, so we want the information of the sun close to us. Even L4 and L5 are farther away to send the data packages back to the relay those to Earth's antennas. So L1 is the most logical choice. It's just where our Aditya is. It's not the nothing more. It's just where the location of Aditya. Okay, so I will talk at length for a couple of minutes about SOOT, solar UV of Aditya L1. So this is team from IUCAA, where I'm currently working, and they made this instrument, packed it inside the rocket, shipped it, and now it is giving us beautiful images. If you're interested, a lot of even science popularization and science ready data is available on this website, so you can quickly go and check it out. So SOOT has several different bands. So each band is at different wavelengths. So these are all wavelengths which are not penetrated in the earth, but we can see chromospheric information from there. So something might be familiar. These are sunspots which are from the photosphere, which we can see using these continuum wavelengths. But then on top of those sunspots, there is something new. So these are the chromospheric filters, or like very precise in their wavelength. The filters are quite precise to tell us, like, at this particular wavelength how many photons are coming at which position from the sun. So these are called Plage regions. These are already seen, obviously, but these wavelengths show us the kind of layering of the sun, which we can kind of patch from photosphere to chromosphere to corona at different heights. Um, there are these few interesting events that had happened in the year of, like, first year of observation from the sun. So there is something called a swirl. So it's basically magnetic twist. So it's like a intertwined rope magnetic rope, and we can actually see that structure here. This is observed in corona, but this is observed, like this observation is in a chromospheric wavelength as well. So we can actually see like something going from lower layer to the upper layer in a magnetic twist. There is this prominence, like one of the other active features of the sun. um, and I'll be showing a few movies. So there are these different wavelengths. One last thing that I should have mentioned before is that all these colors that we see are false colors. So the information that we get in astrophysics, any observatory, tells us the intensity. So everything we see here is in black and white. So we only know how many photons hit the observational plate at a given position at a given time, and that is converted to a black and white image. But then, for one reason which is scientific, and one reason which is just recreational, we usually use filters. Scientifically, we would like to associate some colors. So in SDO, since the other movies that I showed in the beginning, those have been around for more than a decade now, 2010, so 17 years almost. All the scientists, all the solar physicists know that, okay, if we are seeing this golden yellow, it is this particular wavelength. If we are seeing this greenish blue, it is this particular wavelength, and then you associate that with other kind of science. So that is the reason scientifically people color these images, and the other reason is just that they look pretty, and yes, we like colors. So um, so there are these two narrow bands and eight, no, three broad bands and eight narrow bands in which the suit instrument observes. So each has its own purpose. So we'll see, yeah, different layers as seen from the suit instrument. So there was this sunspot which we are actually seeing on top of it, basically, and we can see how it changes. If you want to, oh, does this not play? Yeah. So if you want to see this movie, like it's the full disc, and with each layer we can see like slightly different information in science. So this is just to show the different layers of the sun as seen from suit. uh, yes, so we can also like see this activity happening, and we can trace it, we can understand how this region is moving. For example, here there is this active region moving, there is a large sunspot, and with time how this evolves, how much energy it expands, that we can study using these kind of observations. So this is the full rotation of a chromosphere. So it's very fast temporally, but we can see like several active regions going across. um, we can see like these waves happening in the on the sunspots, and these energy expenditures, energy is being thrown out. We Okay, yeah, there is another example of that here. So if you see, like there is this energy or plasma that moved one from one place to other, and that plasma basically threw out some photons which we could see, and that in that way we know that some energy got transferred. This is one example of a prominence. So prominence is this kind of active feature where we can see like kind of an appendage coming out of sun. This is another example of that. So there is this appendage coming out of sun, it is just staying on top of it for some time, and then it drains back to the sun. Okay, I think that now we are coming to the end. Just wanted to appreciate the team. These are the engineers, astrophysicists, and scientists behind this amazing space observatory. And yeah, I think now we can have questions. And the important thing is to never stop questioning. Maybe I'll stop sharing.
Thanks, Neha. Anybody has any questions? We can take up the questions now. You can raise your hand. Yeah, Rinku. Go ahead.
Good evening, ma'am. Uh, it was very nice to hear from you. It was a lovely and informative discussion. So, you just told that Sun has a differential rotation. It has a, it rotates at equator with high speed rather than pole. So, why does it happen? Uh, I think our Earth has also this kind of rotation. In equator, Earth rotates with different speed uh, other than pole. Is it so?
No, I don't think that Earth has differential rotation. Earth is a solid object, right? So how, like,
Yes.
so if this is a solid object, it will rotate like entirely. It will not have differential rotation. But sun being made of gas, it can rotate differentially. So it and it does. But we do not know exactly why it happens. So one of the simplest explanation is that because the equator is like the longest circumference that there can be, whereas as we go towards the pole, the circles around are smaller and smaller, and then there is momentum built up, so that's why it's faster rotating at the equator. But that is a very crude explanation, because it doesn't explain the entirety of it. It can just give us an intuition, but it doesn't match the figures that we have. So it's the understanding of it magnetically and thermodynamically is still undergoing research. But yeah, that's about it.
The angular velocity of the Earth is same everywhere, but the linear velocity, I think it is different in the pole and in the equator. And you were saying about the sun. I think you were saying about the angular velocity is different. Is it so? In the equator, the angular velocity of rotation of sun is different from the uh, pole. I think you were saying that, na?
No, I didn't mention about any kind of velocity. I said that the number of days it takes to complete one rotation around equator is more than the number of days of the pole.
Okay. And that reason of that phenomena is not still clear. Why
Yes.
it happens? Okay, okay. Thank you, ma'am.
Just to add to that, what Sneha said is about that since Earth is a solid object, whereas Sun is primarily the plasma, the gas form, in gaseous form. So it has that liberty to move, at the equator at a different speed compared to the poles. So that's where basically, at a very crude level, explains this particular phenomena. That's what she tried to explain it. But still, it is uncovered kind of phenomena. What it could be. I mean, still more research has to be done, and then probably we come to a conclusion. And that is why, since the nearest star to us is only the sun, and that is only the opportunity, because all other stars are very far. Studying them is little bit more challenging compared to the sun, and sun is the only opportunity what we have to study one particular type of stars. But there are millions and trillions of stars in our galaxy itself. But the technology what we have today, it also has its own limitations and all the things. So yes, definitely
Yeah.
we need not many
Uh,
researchers like Sneha to come forward and learn more and give us the insight about the stars and the universe. Yes. Anybody else has any question? Thank you, Rinku, for the question.
sir, I have another question. Just,
Yeah, yeah.
uh, sir, always we see the corona, in the North Pole and South Pole, we see the northern light and southern light. Uh, why does it only happen in the poles? Uh, is it the magnetic field is there less strong than the other latitude? Is
No,
it
it's exactly the opposite, actually. I actually touched upon that. Maybe I can explain that again. So maybe Yes, you can see the screen. Good. So what happens is anything that comes from the sun goes in all directions. For example, the solar wind is continuous; it's omnipresent at all times. It is coming out of the sun, and we do not see aurora at all times. Okay, that is first fact. Two facts. One is the solar wind is coming at all times. Second is that we do not see the aurora at all times. So what there needs to be some kind of interaction in between the solar wind and Earth's magnetic field for the plasma that is coming from the solar wind to reach down in the atmosphere of the Earth. Now what happens is, since the magnetic polarities of the Earth is where the magnetic field is stronger, the plasma kind of gets drained inside the near the poles. So it goes way inside in the atmosphere in comparison to the equator, because the magnetic field lines, they will direct the plasma because plasma is magnetically charged and
Okay,
electrically
it will
charged.
follow the magnetic field lines of the Earth.
So
That's
now
why
what
it is.
happens is, uh, when we have like some large coronal mass ejection or some kind of active event flare on the sun, there is a large chunk of plasma which is coming. So if it is a usual less active solar wind, like when the sun is less active, there is always solar wind coming, right? So now as well, but now we don't see. Now we are like, there are less uh, southern lights aurorae in comparison to when there is a coronal mass ejection, because there is less plasma draining. So when there is like large chunk of plasma of the earth, that plasma interacts with the oxygen and nitrogen in the earth, and that creates that green and sometimes pink colors, because then there are these atomic transitions happening in nitrogen and oxygen. Okay, so it's not the plasma that we see actually, we see some wavelength which is emitted by the atoms in the atmosphere. So our atmosphere just gets energized by that. So if there are a lot of this plasma coming, sometimes we also see aurora in Ladakh. If you have seen the news, in December or in last year May, there were these very large events on the surface of the sun, which caused aurora to. So this it's called the auroral oval. That means the region on Earth's atmosphere till where the plasma has drained. So that auroral oval goes near the equator of the Earth if there is higher activity. So people in northern regions of India could see the aurora couple of times last year, but people near the north or south pole, they see more frequently, because that's where the magnetic pole is. Okay.
Okay, ma'am. Got it. Thank you.
Thanks, Rinku. Anybody else has any question? So, Sneha, there is one question from one of our observer, a spectator who is joined remotely. He wanted to know about how do mission INSU payload differs from remote sensing payloads.
Mm, remote sensing payloads. I don't understand.
I mean, the other payloads what we have on the satellites, like cameras, normal cameras, and all the things. They wanted to know
The
more about
instrumentation, they want to understand more.
the INSUT payload. What is there on Aditya L-1? You talked about that on one slide.
So I'm not an instrumentation person. I'm a theoretical physicist. So I only know the theory behind it. I have not worked on the instrumentation. Neither have I indulged into research about that. But I work closely with people who have worked with the instrumentation. And what I understand from that is, for example, we have DSLR camera. We used to have those camera with rolls, and the upgrade was one in the storage of memory and second in the quality of lenses. So it is that kind of instrumentation upgrades that we care about when we are sending the observatories in the space, because we are not going to be able to clean it when it is already in the space. We cannot do anything to it apart from only changing the orientation, uh, like what region on the sun we want to look at or such. From remote, we can only change the science objectives, like the field of view or point of pointing from remotely. So the for example, the observatory on Earth, like Udaipur Solar Observatory, can get an upgrade, changing the lens size or changing any kind of instrumentation in between. The telescope has so many parts. Any of those can be changed at any given point since it's on the Earth. But for space, there needs to be more care in the sense that there cannot be any dust or any kind of thing, like any kind of material chemical that can emit energy, because that will be captured, because the instrumentation is so sensitive that any kind of emission, energy emission, will be captured on the CCDs, is what they call it, the place where the photons convert it into electrons and current, and that current will be recorded as how many photons reached at which pixel, so that we know, like, for example, here. So in this pixel there were less photons, that's why it is darker. In this pixel there are more photons, that's why it's brighter, and so on. So we know, like, how the sun looks, because on the CCD the sensitivity is so high that photons to electrons conversion and then electrons to electronical image conversion is very precise. So we cannot have any kind of dust speckles or any kind of emissions inside the instrumentation. That's one thing. And secondly, another thing is very technical, that this instrumentation is going to be in vacuum, where the temperature is very low. So it needs to be protected from that, and also from the plasma that is coming from the sun, basically, because it doesn't have the shield of Earth's atmosphere. So the heat and the plasma bombardment that is going to be faced by this instrument, that is also taken care of when they design these kind of things.
Okay, great. Anybody else has any question? Gayatri, Samruddhi, Sudhir, Vijay. Vijay, anything from your end? One of our school students,
No, sir.
Rahul, has asked a
No, sir.
question.
She explained beautifully,
Thank,
sir.
yeah, thanks, Vijay.
Excellent, excellent.
Rahul from one of our school students has asked, since sun is so hot, and how does the spacecraft like Aditya will stay close to it without melting?
Um, so Aditya L-1 is very close to Earth, actually. It is. I mean, there is this image that we have, but this is also a cartoon image. It's not to scale. So the L-1 spacecraft is actually revolving around Earth. So yes, not like this, but like this, actually. So it is facing the sun all the time, and as Earth moves along its orbit, it will revolve around the L1 point, facing the sun, and go around the Earth. So yes, sun is very hot, but the definition of temperature, how we measure it. So it is defined based on the motion of particles at that given place. So the plasma that is hot is here, and as we are going away from the sun, the plasma is becoming rarer and rarer. So the definition of temperature itself is a bit tricky to understand. It is not that like, if you touch water, only then you can feel the heat, and if you touch the fumes, you will feel less heat. And if you are like far away, if there is a boiling water, you don't touch the water, you just take the temperature on top of it. But if you're farther away, you will not feel much heat. Still, it is extremely actually it's extremely cold, because it's in the vacuum, and temperature of the vacuum outside is like minus 200, less than minus 200 degrees Celsius. But the particles, if they hit, then it is creating almost like instantaneously it will burn, because it is a high amount of heat that is going to come. So it there are these when it got when the spacecraft was launched, it is quite a lot of rocket science, as they call it, to launch it and to keep it in this orbit, and to prevent it from being burnt or being fried because of these plasma particles. This question might be more valid in the case of Parker Solar Probe, which is actually going very close to the sun. It is even beyond the Mercury uh, planet, and like almost inside the sun, near the corona. So in that case, this question is very valid. That I work on that data, and that is a bit uh, involved answer perhaps, but usually any kind of satellite that goes outside the Earth's atmosphere will face all these plasma, and that's what the instrumentation people take care of. The short answer.
Thank you. Anybody else has any question? We can take up. Arya Malevar, what is L1 point? I think
I
Arya that
explained it a bit
is yes.
before.
You can see in the image also.
Ma'am, one question, please.
Yeah,
Yeah.
Vijay, go ahead.
One question, sir. Whatever we are having now the knowledge of solar physics, uh, when you consider other stars, is this same or intensity changes according to their masses?
Um, so it's a very general question. What so other stars meaning other sun-like stars, then mostly the information can remain same in a very approximate or larger sense, being that the way these layers are, approximately what temperatures these layers can be at, and so on. But then there can be other kind of stars which are very different from sun, even if they uh, in the night sky all the stars basically look the same to eyes, but if we use the good telescopes which can resolve the stars, which can be in which we can see the stars in different wavelengths, then we understand that they have like different structures altogether. Then there are other kind of explosive stars which flare all the time, which are not like the sun. And then there are other kind of stars which are very dark. Uh, those are called brown dwarfs and so on. And then there are even other kind of stars which are very large, like red giants or giant. There is a branch of stars like that. So I don't know how to answer the question, but I think I did.
So basically, just to add what Vijay, it's similar type of star is their sun, so probably more or less they would same. But since we have a huge uh, segment of stars, if you see HR diagram, different types of stars are there. So probably more study is required, but yes, they would have their different type of properties and behaviors altogether. Because if we just compare
Yes, sir.
sun
Yes,
to
sir. Thank you.
Betelgeuse or consider the sun to Betelgeuse or maybe Cyrus, they are huge, huge stars compared to the sun. So, the dynamics and all the concepts and functionality probably would look different. Then again, we are studying only the nearest star to us, but we're trying to understand the star closest to us, but then trying to compare our knowledge and trying to understand those stars. But we still a long way to go and really understand their behaviors and patterns. Thanks,
Yes,
Vijay.
sir.
Thanks for
Thank you, sir.
answering.
Thanks, ma'am. Thank you, madam.
There is one more question in the chat. Currently using suit which type of data files used for data analysis using Python for activities. Going on photosphere, chromosphere, and
Usually it's FITS files, FITS, that is the extension that are most of the observational, uh, mostly astrophysicists use FITS, that's the format. So you can easily access it using Python. There are packages to access FITS files. And yeah, you can download the data from the website that I shared. I think I can flash that up here. Yeah, here, suit.iuca.in. Uh, yeah.
so it's in a public domain, right?
Yes.
Anybody else has any other questions? We have already 6:20 now. Bharat sir, you want to add up something?
I can maybe stop sharing.
Ma'am, last question. What Aditya L-1 has given us the information. What information we have got from the Aditya L-1 mission? Can you brief about that?
Yeah. So there are several studies undergoing. There are a few papers published that you can also access on suit.iuca.in. And a few of those would be about flares. So there are these active events happening on the sun called flares, and so I showed a few movies at the end of the talk, which included these active events. So if how much energy is expended in during a flare, that is usually a concern of research, and this kind of understanding of how much energy is energy expenditure can help us understand the coronal heating problem at some extent. So the flare studies is one of them. Then there are studies happening for the oscillations in the sunspots. So or like any of the layers, there are these oscillations happening. There are waves that can propagate. So these waves can also transport energy across the layers, and those can be one of the ways the heating is happening in the atmosphere. Then there are studies about prominences, and so on. So these are quite involved, and that's why I didn't include the exact results. But you are very welcome to go to the website and check out.
Okay, thank you. Bharat sir, are you there?
Yeah,
To add up? Yeah, please.
yeah. I want to was excellent. Thank you very much. I have a small query for you. Uh, is there any software for Aditya as a tutorial for citizen scientist amateurs who can use Aditya data? It could be as simple as a tutorial which has been done at IUCAA or maybe some other ISRO or some other place. But if there is some kind of a tutorial how to use Aditya data to understand different features, and what kind of softwares would you suggest? I hope
So
it's not too technical.
usually the solar physics data is a bit more technical because sun is very close. So there are more chances for introduction of noise as well in the instrument. So there are constantly workshops happening all over India, how to use the suit data, and I think the recent one was in January in Trivandrum. So people can like attend the workshops and understand. But to the suit team, I will ask if for amateur astronomers, if we have some quick and easy way to uh, like share the tutorials, then they can like sit at home and maybe understand. uh, we can talk about that, but I don't think there exists any as of now. But I will convey this to the team.
Thank you. Thank you so much.
Thank you, Bharat sir. Anybody else has any question further? Or we are good to conclude today's session? Anybody has any questions? No? So, Dr. Sneha, thank
Thank
you.
you
On
so
behalf
much.
of entire team, we would like to express our deepest gratitude for insightful session on the importance of Aditya L-1 in the study of the sun. Definitely, your expertise as a postdoc from IUCAA, ability to simplify the complex topics from magnetic switchback to the sun-earth connections truly inspired to our audience. It was very honorful, and definitely theoretical astrophysics. You're not only champion, but also your outreach programs are really inspiring for everyone. Thank you for your time and passion with us. We look forward following your future contribution to global solar physics. Thank you, Sneha, once again.
Thank you so much. Thank you so much for arranging this, and thank you for having me. and coordinating. Yeah, I hope I inspired somebody at least to pursue solar physics as a career or as a passion. And yeah, thank you, Bharat sir. And thank you for all the questions. They were really nice. It meant that somebody listened to my talk. So it is quite, I'm grateful for this opportunity.
Yeah, I mean, basically, most of the people talk about stars, sun, and night sky and all the things. Somebody talking with respect to the daytime astronomy and solar physics is really, rare things what we have seen. I mean, everybody when they talk about astronomy, they talk about only about night sky, but nobody talks about the sun. So definitely, this is one of thing what we were looking forward, and especially as we are tomorrow celebrating the Women's International Day. So having a female speaker was really inspiring for everybody to look forward and take this subject to study. Yeah. So thank you, Sneha, for once again behalf of Amateur Astronomers Association, and we look forward to you connecting back again in near future with more topics and more time. Thank you.